our next speaker is here, I believe. Yeah, Sam. So it's Sam Cockerill. I hope I didn't mispronounce your name too much. It's the CEO of Libertine FP, a UK company developing linear generator technology for transport and distributed power application. He started his career making race engines, like Cosworth in Northampton, and before forming Libertine in 2009, he was member of the senior management team of Ensus, one of Europe's major bioethanol producer. Welcome, sir.
Very good. Well, firstly, thank you to Jamie and to Amani and to the organisers at the KAUST event for the opportunity to visit KAUST and to speak in person today. The hospitality has been fantastic, and it's been a really exciting crowd to be involved in. So yes, I'm going to talk about linear generators. By linear generator, we mean opposed free piston direct injection uniflow scavenged two-stroke engine, but that didn't make it past the marketing department. So linear generators. Let me just first describe with a short video how a linear generator operates. So you'll see here inside the combustion chamber, we have two opposed free pistons, but we don't have any connecting rods and we don't have any crankshafts. Instead, we have these linear electrical machines. We have gas springs on either end, we have bearings and encoder systems and so on. And their job is to control very precisely the motion of the pistons to achieve in real time the compression ratio that's required according to the combustion method, according to the transient operation, and according to the emissions requirements or efficiency requirements of the operating point. Now, the focus of this presentation is going to be on the heavy-duty powertrain applications of this technology and how Libertine's electrical machine and control technology platform enables the creation of this new type of power generator product. Now, we're talking here about hydrogen, and specifically hydrogen-opposed piston engines, and to many at KAUST, this will be a very familiar area. KAUST is a member of the hydrogen-opposed piston engine working group, and there are some really specific benefits of using hydrogen in this combustion architecture. And they span efficiency, nitrous oxide emissions, and cost. So efficiency is derived in this architecture from the elimination of the thermal losses from the cylinder head and from the valve train friction, because there are no cylinder heads and there is no valve train. The valving is achieved through porting. Secondly, some technical reasons why low nitrous oxide emissions, low engine out nitrous oxide emissions are possible, in part because two-stroke is an inherently power-dense format. So the system can operate lean with lower BMEPs for the same output, for the same torque. There's also the possibility to use the uniflow scavenging and the boost actuation to dynamically control internal EGR, which is another lever by which nitrous oxide emissions can be controlled. And low cost, of course, is achieved through the elimination of the cylinder heads and the valve train components. So as a combustion architecture, this is a very fit architecture for using hydrogen as a fuel. But the next question is then, well, how does achieving this format with an opposed piston construction, with a linear generator free piston construction, provide further benefits? And there are some very substantial further benefits here. So without the crankshafts, we have real-time compression ratio control, which provides fuel flexibility, clean cold start and transients, and stable homogeneous charge compression ignition. And today, commercial linear generators are in operation in the US, a company called Mainspring, which achieve these benefits and demonstrate that this is possible. Secondly, there are some duty cycle performance benefits. So it's possible in the same engine now, because you are not committed to compression ratio, it's possible to have the same engine delivering a genuinely mixed mode, spark ignition stoichiometric, lean spark ignition, compression ignition, HCCI, all in the same device. These are now just operating points. These aren't different engine types. It's possible to achieve full cylinder deactivation, which gives some very interesting potential for achieving peak efficiency right the way across a range of operating points, certainly with 50% turn down. It's also possible, thanks to this combination of position information, acceleration information, and current information, to infer everything that's happening inside the electrical machine, inside the free piston movement system, which provides very rich diagnostic data for AI and machine learning. The oil-free there's potential for oil-free operation because we don't have main journal bearings, we don't have a piston skirt that's required to resolve piston forces into a torque, so we can operate without oil. And again, this is something that Mainspring have done, which provides lower maintenance. It allows higher wall temperatures, potentially adiabatic operation, which is very exciting. Reduces the tendency of oil droplets to cause knock or pre-ignition, and potentially eliminates the requirement for a particulate filter. Other benefits include the efficiency derived from very rapid expansion, which lowers heat losses, very compact packaging through the elimination of the crankshafts, and ultra-low vibration start-stop operation, which certainly in passenger applications is another important differentiator. So we're very excited about the complementarity between free piston and opposed piston combustion, which then begs the question, well, if this is so good, how come this isn't in widespread use today? I've mentioned the company in California that are doing this, but for that one company, there are 10 or more companies and research organizations who, over the past few decades, have not brought the technology out of the lab and into production. So the question is, why hasn't this been done so far? There are a number of reasons for this, and specifically related to the technology environment. So the power electronics haven't been there until now. The electrical machine performance hasn't been there until now. The controllers that are required for the engine and the electrical machine control performance through integration, that integration hasn't been possible until now. And the system integration more generally, and the delivery of the optimized performance that can only be achieved when the electrical machine, the combustion system, and the controls are co-optimized, that hasn't been done until now, which means all of the benefits that arise as a result of real-time compression ratio control have not been available until now. And this is Libertine's business. We're a relatively small company in Sheffield, but we focus on delivering those benefits, realizing the benefits of the technologies that now exist to help companies and research organizations explore and extract the benefits of this new and exciting architecture. So Libertine develops, manufactures, and licenses a platform technology for linear generator product development. Of course, linear generators, we're very excited about, provide clean, efficient power generation using a wide range of fuels, including hydrogen, but also can be software configured for a range of different fuels, even in the same device. The flexibility to use existing fuels like natural gas today and to use green hydrogen in future in the same engine. This is a very strong differentiator for this technology. And the platform specifically combines high-performance electrical machines, high-performance power electronics, motion control systems, and developer tools to accelerate the path to the creation of linear generator products. We have two models through which we do this. IntelliGen is a proposition for OEMs to help accelerate their product development. And OpenFBE is a research tool, a bit like a Ricardo Hydro research engine, that provides the means to research organizations to explore this new white space of the art of what is possible when real-time compression ratio control is part of the calibration parameter set. Now, just to navigate this talk, to navigate what I'm going to describe today, this is where we think linear generator technology will go in terms of performance and cost. So today I'll be talking about the proof of concept prototype, the smaller 20 kilowatt system we've been developing and demonstrated with Mile Powertrain in 2020, 2021, and how that's led to the creation of a larger, more capable, longer duration operation for a performance validation prototype for heavy-duty powertrains, so specifically the LGN 120 P1 system, apologies for all the acronyms. The second generation system, the P2 system, we just had on stand at the ASME event in the US recently. And this gives more of an indication of where we can go to with packaging for vehicle demonstration. Again, realizing some of the very significant benefits that are possible when you don't have crankshafts and you don't have all that mechanical bottom end to contend with. And then in the roadmap, we look further ahead to why an OEM might invest in this technology. The full potential of linear generators, we think, is strongly differentiated, achieving the cost and the durability of conventional engines, but providing the efficiency of fuel cells, and crucially, providing the fuel flexibility to make use of existing fuels today and to open the path to low and zero carbon fuels of the future. So this is where we started. This is the proof of concept prototype that we took to Mile Powertrain, and you'll recognize some similarities to the earlier animation that I showed you. Inside, we have an opposed free piston combustion system. We have the two gas springs on either end that are storing some of the combustion work. We have these two electrical machines that are providing the control and providing the means to achieve this very precise compression ratio cycle by cycle. And we brought this onto the test cell right in the middle of COVID. So we developed this during 2019. We brought it to model powertrain at the end of 2020. And we integrated into the test cell to demonstrate the key attribute of our technology, which is with even the trickiest of fuels. We used hydrous bioethanol because it tends to misfire at cold start. And even with the variation inherent in this combustion fuel and the method we were using, we were able to achieve very tight control of compression ratio. So we've demonstrated cycle by cycle, small variations that previously have really destroyed the combustion stability of free piston systems. Small variations, in our case, lead to even smaller variations in compression ratio. And this allowed us to demonstrate, in the case of hydrous bioethanol, reasonably good indicated thermal efficiency, but crucially, very consistent compression ratio control. Now that got us thinking, where could this technology be used? Today, as I mentioned, linear generators are used in distributed power generation at the relatively large scale, 240 kilowatts and above. But if we look at the total addressable market for this technology, it goes well beyond the distributed power applications that have been targeted by the company that I mentioned in the US. And in particular, in heavy-duty powertrains, which includes commercial vehicles on highway and off highway. These are some of the largest applications. So our next step was to look at how we could take our motion control performance and apply that in a format, in a package that could be used, would be relevant to heavy-duty vehicles. Now, my family firm operates a fleet of heavy-duty vehicles, and they're all diesel-powered. And the reason for that is the impact of battery electrification on payload and productivity means battery electric trucks are not economic for us, nor for any operator like us in the UK. Range extension, an onboard thermal power generator using widely available fuels, could address that barrier. And it addresses the combination of those barriers by allowing a smaller battery, so there's not so much impact on payload, and removing the requirement to come back to base every day or to take off-route miles to go and get recharged more frequently than we're refueling at the moment. So by eliminating the payload cost of very heavy batteries and reducing unproductive miles and hours, and also reducing the additional cost of having perhaps a 1 megawatt hour battery on board the trucks, which is what they would need to do what they do today, range extension addresses the barriers to electrification in heavy-duty vehicles. Now, there are a number of range extension technologies. We've talked in this conference about conventional hydrogen internal combustion engines. It's also possible to use fuel cells, solid oxide fuel cells and PEM fuel cells to achieve the same thing. But if we look across the metrics that count, fuel flexibility, durability, and capital costs, we see actually it's only in the case of fuel flexibility, solid oxide fuel cells that can genuinely achieve the flexibility to use natural gas and hydrogen. In the case of a conventional crankshaft-based internal combustion engine, the fuel flexibility is limited because the compression ratio has to be set essentially by hydrogen at a lower level than would be optimal for compressed natural gas. Similarly, PEM fuel cells require ultra-high purity hydrogen. So fuel flexibility reduces the field to linear generators and solid oxide fuel cells. And comparing these two technologies, solid oxide fuel cells today have challenges around durability because of the high temperatures involved. And even in the long term, we've not met anyone who believes solid oxide fuel cells can be brought down below about $200 per kilowatt. Linear generators are potentially 4 times less expensive than that in terms of capital cost. And that means that technology is going to be much more relevant on a widespread basis. So with that insight, we set about developing the performance validation prototype you can see here on the right-hand side. Compared to the proof of concept prototype, this is a larger system. It has a 107 millimeter bore. And we chose that bore in common with a lot of existing heavy-duty vehicle engines today. So we have a good choice of ring pack and other combustion equipment. It's a multi-cylinder format, specifically 2 cylinders in this case, but it can be multiplied out to 4, 6, 8 or more cylinders. It has much more efficient electrical machines we've developed. It operates on gas bearings rather than dry bearings. we're using Mahler Powertrain's internal combustion systems. Now, bear in mind, we're not a combustion development company, but we deliberately provide our platform technology to allow third parties, to allow OEMs to develop their own combustion systems and integrate to create their own linear generator products using our platform technology. We've got better cooling. We've integrated the system into extruded housings that provide very concentrated and low-cost cooling systems. We provide a longer duration and test capability, and we use fuel-flexible hydrogen CNG direct injection fuel injectors from Clean Air Power. Now, just looking at what we've done on our side to enhance the platform, I've mentioned it's a multi-cylinder architecture with high force, more efficient electrical machines and integrated gas bearings. But a key part of what we've been doing to support this new development is on the control and software side. We now use model-based profile shaping and control optimization to define the motion profiles that permit very efficient and very precise motion control. And how we do that is through the analysis of the data. And this is data that came off the proof of concept prototype. What I've plotted here is acceleration over position. All of our data we typically think of in the position domain rather than the crank degrees domain. There is no crank. And in the position domain, acceleration and inertial force are one and the same thing. They're just related through the moving mass. And although this is a bit of a sort of weird shaped curve, there's a few non-linear features here. It's very repeatable. If you look at the individual cycles that make up this average cycle, they're all very close to the information we see here in this average cycle plot. And we can disaggregate this into the contribution of the electrical machine. In this particular average cycle, this is a single stroke. In this particular stroke, the electrical machine is not doing very much. It's sort of cycling between motoring and generating. But if we subtract the electrical machine force from the inertial force, we reveal what we call the aggregate mechanical force function. And that describes everything else mechanically and in terms of gas forces that's happening inside the linear generator. So we can disaggregate that in what we call our CKC model, our chamber kinetic control model, into the constituents, the combustion model, the main chamber force function that's typically created through combustion modeling. The bounce chamber force function, a bit like the combustion force function, but there's no combustion going on. That's just a slightly lossy compression and expansion process. The friction and pumping force functions, there are actually a number of distinct friction functions that relate to viscous friction and static friction and so on. And they can each be described in the position and the velocity domains. And then on the right-hand side, we have the electromagnetic force function, and that's bread and butter for us. That's our core business, understanding and controlling how electrical machine force is applied through the application controller or the engine controller asking for an operating point, through our motion controller delivering the compression ratio and the profile involved, the e-machine turning that profile and the demand signals into the force that's produced by the electrical machine. And in combination, each of those readily described functions produce the acceleration that we can then observe and interpret from the linear generator. I've skipped over the residual term here, and this is actually the most interesting part of the whole model, because this describes everything that's changed or everything that's wrong with the other boxes. And so that single residual term becomes the most valuable source of diagnostic information as things change during the course of a run or during the course of the wear or operating life of the whole system. And this is why this 1D simulation environment, this tool, is so powerful. It can be used right the way across the product development cycle and through into operation and to end of life for a linear generator, which includes conceptual design, making sure that the combustion method is well aligned with the capabilities of the electrical machine. The hardware design, selecting the motion profile that provides the best balance of combustion efficiency and e-machine efficiency. In control development, we can port the same Simulink model into a real-time hardware-on-loop test system that allows us to validate the control gains and the control performance before we get into hardware and start bashing things around and breaking stuff. And then during operation, we can interpret what changes in the residual term to see what that means in terms of the thermal performance, the sealing performance, and any degradation through the life of the system. So that's our stuff. Just conscious of time, I'll move on to the Mahler Powertrain development. So Mahler have developed their own internal combustion systems here, and I've just shown the scavenging model that they created to improve trapped residuals and the scavenging performance of the system. And this really reveals how our platform technology can be used in the hands of OEMs in their development programs. The combustion system there on the bench, another short animation just showing how the Mahler combustion system marries together with our electrical machines and the two-cylinder system, and the ends really do flash. So a bit of a gimmick, but I'll show you on the next slide the second generation system. I'll just skip through a couple of these. So the second generation system developed for vehicle demonstrations. We took to the ASME ICEF event. Now this is a bit of physical hardware, it's not functional. I wonder if the animation will play. Oops, are we frozen? I'll go back. No, not to worry. So the intent with this second generation system, this mock-up we took to the stand last week, is to show just how compact this system can be. So everything that you can see here corresponds to the bare generator set in a conventional engine, but the whole system, generating in the region of 120 to 180 kilowatts, is packaged within a height of about 200 millimeters. Now, of course, that doesn't include the intake and the exhaust system, the e-turbo and the power electronics that are packaged to sit closely adjacent to this. But it shows the art of the possible. And we think that the very modular and compact nature of linear generators, the close integration of the electrical machines and the combustion system itself, gives another very strong reason for the manufacturers of electrified powertrains and series hybrid vehicles to think carefully about including technology like this in their roadmaps. In our roadmap, we look ahead to 2025 and beyond as the likely timeframes for the advancement of the technology through vehicle demonstrations, through our partner programs and their performance validation, and ultimately through productionization, manufacturing development, before we expect linear generators to play a major role in powertrains globally by the end of this decade. As a company, I mentioned, we're a very small company based in Sheffield. We're now up to 20 people. I think this time last year we were 10 people. So we're, from our perspective, we're growing relatively quickly, but and supported by a small IPO we did last year. We have been around for over a decade now, and much of that time has been proof of concept development and IP portfolio development, but very much accelerating since 2017, when we established our facilities in Sheffield, and since our IPO, when we've had the means to scale up the engagement with companies in the US, in India, and worldwide, where the need for linear generator technology and the market imperatives are very much aligning with the technology that's now available to create new linear generator products. So just to wrap up then, I've given apologies for a rather quick canter through the technology. We're very excited about the technology category and the position that we're now in to help companies bring this technology to market. In heavy-duty hybrid applications, we think this could play a major role in accelerating electrification and decarbonization of transport through renewable fuels like hydrogen, but by making sure that these powertrains today can be used with existing fuels. And so with that, I'll wrap up the presentation and take any questions. Before I do, just a quick acknowledgement to Mahler Powertrain, who have provided their expertise and their input to create the combustion systems that I've shown you today, and also to our control development partner in the US, Filitech, who are supporting a lot of our expansion and control development work with US partners. So thank you very much.
Any more questions?
So this is a great presentation. Just wondering, like for a given bore diameter, it appears to me from the pictures, the aspect ratio of the entire engine is pretty bulky. I mean, when I say bulky, it's lengthy, let's put this way.
Yes.
So if I consider a current engine with all the packaging, etc., so it's, I mean, I would see like it's compact because of the developments over the years. This appears to be, it will take some more time, like maybe another 10 years, 15 years to bring to that compactness. Is that correct? Is my understanding correct on this?
So it's certainly true that there are more power dense technologies out there. So power density, I don't think, is a strong differentiator of linear generators. It's also the case because the electrical machines are being forced to stop. They have to make do with this varying velocity profile, right? So that's not a great environment for electrical machines. Typically, electrical machines work best, they're most power dense, when they have a constant high rotating speed. So we don't have that, which is why, compared to a conventional generator set, where the electrical machines are typically smaller than the prime mover, in this case, the electrical machines are maybe twice the size of the combustion system. So, we have to take that on the chin. That's an inherent part of what a linear generator is. But the payoff from that is we achieve compactness in terms of not having crankshafts, right? So to take an example in the US, Achates make an opposed piston system. If Achates remove the crankshaft and replace those with electrical machines, that will be a more compact system, because even though the electrical machines are more bulky than a conventional generator, the saving in terms of the crankshafts and the whole bottom end more than offsets that.
Thank you. And another question is, you mentioned about the fuel flexibility. Perhaps if you're trying to use hydrogen versus something else, like for example, a natural gas, I would assume like you have to have a choice of materials in order to, handle the embrittlement or any other corrosion activities of these fuels. If you're designing for hydrogen, obviously you are going with expensive materials, right? Compared to a natural gas or a diesel, any other fuel, a methanol, something like that.
So the key material consideration for hydrogen sits inside of the fueling system, where the pressures and the pure hydrogen make that quite a hostile environment. So we work with Clean Air Power, who have hydrogen, CNG, dual fuel, direct injection fuel injectors. And the opportunity there is to create a fuel system which has just a single fuel tank that you can put hydrogen into, but you could also put a lower pressure of CNG into, a single fuel rail and a single set of fuel injectors that can deliver either of those two fuels. I think from our perspective, the challenges of hydrogen integration are, they're engineering challenges, but they're well known to us. In fact, I've not talked about it in this presentation, but in the US, we're working with Southwest Research on a hydrogen compressor, a pure hydrogen compressor, taking as part of a 700 bar hydrogen refueling system. So there, the electrical machine and our encoder technology sit inside of the high pressure hydrogen envelope, and we've engineered solutions there.
Thank you. Thank you very much.
Thank you.
Nice presentation. Just a quick question related to your technology pathway to the improved efficiency, a way forward beyond 37% that you show. What sort of ideas do you have that will get you to the very high efficiency numbers?
So part of what gives us confidence that those high efficiency numbers will be possible are the existing commercial performance of mainsprings linear generators, which, although they're quite tight-lipped about their efficiency numbers, we think just based on the economics that their customers see, their efficiency is in the region of 50% from fuel to electrical power. Now, in addition to the inherent combustion efficiency advantages of opposed piston combustion, the linear generator achieves further efficiencies in part through the very rapid expansion ratio, so that because you're spending less time at the very hottest part of the cycle, that delivers some efficiency benefit. There are efficiency benefits through the reduction or elimination of the sliding friction and the pumping friction associated with the bottom end of the engine. In future, there are potentially efficiency gains that come through increasing wall temperatures, because if we can move to an oil-free operation, then wall temperatures can be allowed to rise, and we can have something approaching an adiabatic engine. There are also, I think, as a consequence of raising combustion chamber wall temperatures, more of the heat that's rejected is then present in high quality form in the exhaust. So that lends itself to more effective waste heat recovery integration as well. Perhaps not relevant for powertrain applications, but certainly in distributed power applications, the potential to integrate the kind of internal combustion together with an organic Rankine cycle or a Stirling cycle, or perhaps even a cascaded system for heat recovery, that could take us to really very interesting levels of efficiency. So, and I think those considerations will be slightly different for hydrogen compared to CNG, because optimizing those two fuels will likely require different compression ratios, different stoichiometry. But again, the flexibility of a linear generator allows each of those combustion methods and those fuels to be co-optimized without one constraining the other.
Yeah, thank you very much for the presentation. Just a quick question: would it be possible to have 4 pistons instead of 2 for the power generation? Thank you.
So yes, so in terms of multi-piston architectures, so you could take the opposed piston construction with 2 cylinders and then have more cylinders. It's also possible to realize opposed combustion architectures, and you might be familiar with the work that Volvo and others have done with opposed combustion architectures, where you could have, if you could achieve a complete balanced system with 4 pistons, each having 2 combustion chambers, 1 on either end. And that, I think, is likely to be a power dense solution, but not a very efficient solution, because to achieve the same fully balanced operation, you take a single central combustion chamber, and now you have to divide it into 8 separate combustion chambers. So just the surface area to volume there counts against you. But I agree that's possible. And I think we're keen to work with OEMs to help them realize the combustion architecture that makes sense in their particular applications.
Any more questions? Now let's thank